And this is the title of my presentation. I'm going to talk about the mechanical behavior of the carbon fiber reinforcement polymer. And this polymer that I will talking about is the thermosetting matrix using statistical analysis and neural network. So carbon fiber reinforcement polymer, or just this to the conventional metallic components, and we are seeing the growth are working now with this kind of urban air mobility here in Brazil with Embraer. So here we have an exponential increase of carbon fiber composites. For this designer, we are looking for to apply 100% of composite and its structure. So we are looking for, especially for a more complex, that exhibits an interesting option regarding the weight reduction of the carbon fiber composites. And this process could carry out a 3D complex geometry without sacrificing the structural performance. In this image, we have an example of an additive manufacturing processing, the FFF based in 3D printed fused filament fabrication. Here we have the injection, the printing direction, and the composites. This printing direction carry out continuous carbon fiber and epoxy resin. So the main problem we have for this application, it's not possible yet for structural components because we have a large presence of porosity between the filaments. This porosity is detrimental to mechanical performance, even being a suitable way to perform a fluid transport, but for structural application is not so good because we have a limited interaction area between the filaments, in which decrease the shear in all directions, and becomes the lamination is more prone in these regions. So the mechanical behavior of these components is too low for structural application. Just for information, usually the conventional materials, the conventional composites for structural application, we have the concern to have lower than 2% of porosity, of void fraction. And this kind of material, we usually have 2% until 15%. It's too high for application. So this work we are performing is to avoid this kind of defect. The porosity in 3D printing is very complex. We have interporosity between the filaments, intraporosity inside the filaments, and we have porosity, different porosity in this region that we have a change in direction of the printing sections. So for this work, we are going to talk about this porosity between the printing filaments. So here we have another view of the scan of the 3D printing. We have the filaments and the interprinting porosity, or the voids between the filaments. The first try we're going to try is to overlay the printing section. So this is an important way to reduce between the filaments. However, we have an appropriate overlay, because a lower overlay, we will increase these voids, and a higher overlay, we can change the geometry and change the fiber direction, which is also detrimental to the mechanical performance. Another parameters that can change or can avoid inter-voids defect is the printing speed. Since when we have a lower speed, we have accumulation of the material in the outside of the impregnation, increasing the diameter size. And if we have a higher speeds, we will have a elongation of the inside porosity with the printing speed, the thickness, the space between the vertical direction and the space in the horizontal direction. So the aim of this work is to generate a mechanical behavior prediction of a carbon fiber composite processed by 3D printing. For this purpose, I will use the artificial neural network combined with the response surface methodology to optimize the processing parameter to ensure the high mechanical behavior. For this project, we use the carbon fiber, the unidirectional carbon fiber from Tenax and the epoxy resin from Solvay Group. The first step was the processing, where we change the levels of the processing parameter, the speed level, the space, horizontal space between the printing section, the thickness, the vertical space between the printing section, the cure temperature, and vacuum pressure. We processed 20 laminate composites. After that, we proceed the mechanical test, the 3-point bending test. And finally, we apply the artificial neural network and response surface methodology to create the prediction section. So the results, I don't have many time to explain the scheme of ANN, but we have the inputs. That was the processing parameters. After the mechanical behavior, we performed in the hiding layers with a non-dimensional parameter, the weighting algorithm and activation functions to predict the mechanical behavior, the flexural strength, the flexural modulus, and the flexural strain, the deformation of the material. So here we have the processing parameters level for each laminate. We have 20 laminates, in which we change the speed, the space, the thickness, the cure temperature, and the vacuum pressure. So this is the results, the experimental results of flexural strength, modulus, and deformation. And here we have the prediction results. And we have a very similar results between the prediction and experimental with error lower than 1%. So this is a very good method. And here is the confirmation of that. We have the ANN regression plot. We have a linear regression with R square very high. Here we have the experimental results and the prediction section. And after that, with this, we can change the parameters level and predict the response, the mechanical behavior. However, to active the best mechanical behavior, we have to change a lot of combination to results in the best mechanical behavior. For that, we perform the response surface methodology, in which we combine different two parameters levels to reach the mechanical behavior. So here we have the space and the speed, and here we have the thickness versus the space. So here, for lower space and lower speed, we have the higher mechanical behavior, because we have an overlayer here, and we have an increase in the diameter here with the low speeds. And here the same. And for cure temperature, is the most appropriate value to increase the mechanical behavior is the intermediate cure temperature with intermediate to the highest vacuum pressure. This result was for the RSM strength, and for the modulus is the same trend. For the deformation, we have an opposite behavior, because the porosity acts as a stress concentrated for the modulus and the mechanical strain. However, it's facilitate the deformation. So with higher porosity, we have a higher deformation capacity. So if you want to apply this kind of composite with higher deformation, this graph could be help. You can choose the most appropriate parameters here to have a higher or a lower deformation. And to conclude this work, this research firstly reports the processing parameters, and we evaluate the influence of these processing parameters in mechanical behavior of 3D printed composites. The artificial neural network proved to be a feasible method to predict the mechanical behavior of these composites with lower error than 1%. And the mechanical behavior of RSM is a feasible method to determine the optimal mechanical performance regarding the specific application. In other words, you can choose the parameters levels and reach and find your mechanical behavior, deformation, or strength just using this information that we provide. These are some reference that I used. Here is the internet. If you want more explanation or any question, I'm available. Thank you very much.